Awesome. So I'm going to get started here, guys. I want to wish you guys all good afternoon, and I want to thank you all for taking the time to tune in and join us today. I realize that a lot of you may be tuning in from different time zones all around the globe. So I just want to express a warm welcome and thank you for tuning into the first installment in the Innovations in Pipeline Engineering webinar series. I'm going to keep my discussion here very brief today, as we want to provide Dr. Emilio Martinez-Paneda with as much time as possible to cover his subject. But a couple housekeeping items before we get started. So you're gonna have me for another minute here. I'm gonna run into an introduction into Northern Crescent, what we do, and sort of why this webinar series got created. I'm then gonna hand it over to Jan, who's YPAC's incoming president, and he's gonna introduce you guys to YPAC and sort of some of the exciting things they've got going on. We're then gonna have an overview of Northern Crescent's R&D initiative on hydrogen embrittlement, hosted by our very own Dr. Farhad Devirapur. And then the spotlight is going to be turned entirely to Dr. Emilio Martinez-Paneda, who's going to be the star of the show today, who's going to do his presentation on virtual testing of components subjected to hydrogen embrittlement and stress corrosion cracking. If you guys have any questions at any time today, please feel free to use the chat functionality in the Teams webinar. Our very own Dr. Shama Roy will be filtering through those questions, and he will host a Q&A session with Dr. Martinez-Paneda at the end of the presentation. So who are we? What is Northern Crescent? What do we do? For those of you who have not been introduced to us yet, we are a local multidisciplinary engineering company operating out of Calgary, Alberta. We are a young team of professional engineers and PhDs specializing in the niche field of pipeline stress and pipeline integrity. It's thanks to this background that we are very excited to bring you all this discussion today, and we're looking forward to making this a monthly staple moving forward. With that, my time is up. I'm going to hand the microphone over to Jan, YPAC's incoming president, to introduce YPAC and some of the exciting things they've got moving forward. Jan, over to you.
Thanks, Patrick. Hi, everyone. My name is Ian Sugg, an incoming president at Young Pipeliners Association of Canada, so-called YPAC. We are very excited to partner with Northern Crescent for this webinar series. And for those of you who are not familiar with YPAC, we are a professional association for early career individuals in the pipeline industry, with the vision to build a next generation of pipeline industry leaders. Today, we have more than 2,000 members with 11 chapters in 9 cities across Canada from coast to coast. And we are always looking for new members and volunteers. So you can learn more about us on our website at ypacanada.com. Today's event will be the first of the many webinar series we'll be hosting in the future, so stay tuned. Thank you, and I will now hand it over to Farhad.
Thank you, Jan. Let me share my screen. So just before I start, I want to make sure that you guys could see my screen. Patrick, could you confirm, please?
Yep. I can confirm.
Awesome. So, hello everyone. My name is Farhad Devirapur. I'm a postdoc fellow at Northern Crescent. And in the next slides, I'm going to introduce the hydrogen initiative that our team at Northern Crescent has started. Just before jumping into hydrogen embrittlement, in this slide, I would like to present a brief overview of opportunities and challenges that come with building a hydrogen economy. From the opportunity side, hydrogen is the most abundant element in the universe, and its pure form could be extracted from varied resources such as natural gas or water. When it's burned, it produces energy and water as the only byproduct, which makes it a suitable energy source for 2050 net zero emission goal. In this respect, it's estimated that by 2050, near 24% of global energy demand will be supplied by hydrogen. Also, another significant opportunity is that in a hydrogen economy, the existing pipeline infrastructure could be leveraged to carry hydrogen. For example, like blending hydrogen into existing natural gas pipelines. However, in terms of challenges, hydrogen is a small particle and can diffuse in a steel. This could reduce the ductility of a steel and poses a threat to the structural integrity of pipelines, especially high-grade pipelines. This phenomenon is termed as hydrogen embrittlement. It's worth noting that in the area of hydrogen embrittlement, there are very few publicly available physical test data and limited numerical simulation techniques. At Northern Crescent, we are developing advanced numerical tools in Abacus to predict hydrogen embrittlement in steel pipes under varied exposure to hydrogen concentration and using different techniques, especially the phase field fracture method. In this slide, a benchmarking example of a 2D notched square plate is presented, which is based on the work by Martinez et al. 2018, who is the main speaker in our today's webinar. The figure on the left shows the plate, which is fixed at the bottom and pulled from the top, and the video in the center shows the initiation and evolution of the damage, and the right figure presents the force displacement curve for scenario with no hydrogen, which is the blue curve, and the one with 0.5 ppm hydrogen concentration, which is the green curve. As you can see, with 0.5 ppm of hydrogen concentration, it leads to around 50% reduction in the load carrying capacity of the plate, which demonstrates the significant effect of hydrogen embrittlement in steel. This slide also shows two other benchmarking examples where the steel is exposed to hydrogen. The video on the left shows the damage initiation and evolution in a 2D compact tension or CT specimen, and the one on the right shows the damage in a single edge notched tension specimen or SENT specimen. Using our in-house numerical tool, we were able to predict hydrogen embrittlement in these examples. So here I finished the introduction to our hydrogen embrittlement initiative. Please feel free to send a message or email to me or or the other team members, Dr. Shama Roy or Dr. Sylvester Agbo, if you have a question or if you have an interesting idea and you would like to collaborate with us. Now, before handing over the floor to Dr. Martinez-Paneda, the star of our webinar, I would like to introduce him. Dr. Emilio Martinez-Paneda is an associate professor in mechanics of materials at Imperial College London, where he leads the mechanics of infrastructure materials lab. Prior to joining Imperial College as an assistant professor in September 2019, Dr. Martinez-Paneda was an 1851 research fellow at the University of Cambridge. His research interests span a wide range of topics within applied mechanics, from chemomechanical fracture to small-scale plasticity. Dr. Martinez-Paneda has published more than 50 scientific papers in the best journals of the field and received numerous prestigious awards and fellowships for his contribution. Now I hand it over to you, Dr. Martinez, and I'm looking forward to hearing your amazing presentation. Thanks.
Thank you, Farhad. So let me just share my screen. Can someone confirm that you're seeing my screen full screen?
Yes, I can see it.
Thank you so much. Well, thank you, Farhad, for this very kind introduction, and also many thanks to all the organizers for putting this together. It's a great pleasure to contribute to this first seminar on this seminar series on innovations in pipeline engineering. So yeah, as you heard, my name is Emilio Martinez-Paneda. I'm an associate professor at Imperial College London. And what I want to talk about today is basically, I want to show some advances in computational modeling and scientific understanding of hydrogen embrittlement and stress corrosion cracking. And I think that this is important because these advances in computational modeling and scientific understanding has enabled us to be able to develop tools, computational tools that allows us to predict when these phenomena are about to happen. And this, of course, has very important implications for design, operation, and management of pipeline and many other components, of course. So before I start, let me clarify a few things regarding the terminology. So within the broad term of environmental assisted cracking, we have multiple categories, one of which is stress corrosion cracking. And stress corrosion cracking can be divided into two groups as well: anodic dissolution cracking processes and hydrogen embrittlement. And you will see that hydrogen embrittlement appears twice in this slide. Well, the reason being, of course, that You can have hydrogen embrittlement in a corrosive environment where hydrogen ingress is a result of the corrosive reactions. But you could also have hydrogen embrittlement in the absence of an aqueous electrolyte, for example, when you have components exposed to hydrogen gas. And my talk will have two parts. The main part, the first part, will deal with hydrogen embrittlement in a general sense, so for all environments. And then the second part, a shorter one, will deal with stress corrosion cracking phenomena driven by anodic dissolution processes. So this could be more anodic driven stress corrosion cracking. So let me start with the hydrogen embrittlement part. And hydrogen embrittlement is actually quite an old problem. I mean, it goes back. We know that hydrogen and metals are not good friends, and we know this for more than 100 years ago, right? We goes back to this paper from Johnson in the Proceedings of the Royal Society in 1875. And as you can see in the slide, he writes about some remarkable and extraordinary decrease in fracture toughness and breaking strain in iron and steel in the presence of hydrogen. And in those days, you will very rarely see words such as remarkable or extraordinary in scientific papers. But the truth is that the effect of hydrogen in metals is quite remarkable and extraordinary. So one of these effects is how the ductility of metals is reduced by the hydrogen content. You can see this here. These are uniaxial stress strain curves. And you can see that if you introduce hydrogen into your samples, for example, exposing them to hydrogen gas, you see a very dramatic reduction in the failure strain. Another effect is this drastic reduction that you see in fracture toughness whenever you expose your metallic samples to hydrogen. You can see an example here. So this is I think it's a steel that failed that has a fracture toughness of 150 megapascals a square meter. And you can see that as you increase the hydrogen content, it fails at toughnesses below 40 megapascals a square meter. And this is for a low strength steel. In high strength steels, this reduction in the fracture resistance can be of up to 90%. And this is a key point to emphasize. The susceptibility to hydrogen damage increases with the strength of the material. You can see here fracture toughness versus material strength. This is for a given environment, so you can think of seawater. And if you notice that materials with alloys with very high strength will fail at fracture toughness below 10 megapascals a square meter, so almost like a ceramic. And this is a very important point because this picture is providing us with two takeaway messages. The first one is that hydrogen is compromising decades of metallurgical research. So we have developed high performance materials, but we cannot use them. And then the second one is that with modern alloys, we are seeing hydrogen assisted failures in many applications and sectors that we never heard about before. So little hydrogen is enough to cause trouble in these more susceptible materials. So traditionally, hydrogen embrittlement was a problem related to aggressive environments, such as those relevant to offshore engineering. But of course, we want to use high-strength alloys. We want to use these modern alloys because they are cost-effective, because they solve many of our problems. And we want to use them in our cars. We want to use them in our bridges. We want to use them in our buildings, in our railways. And this has triggered numerous hydrogen-assisted failures. You can see an example here. This is a famous newspaper in the UK. This is one of the most famous skyscrapers in London, and you can see that the newspaper report these hydrogen embrittlement issues. And as you see, this happens in very inert environments. We don't need to be surrounded by H2S anymore. The water vapor is enough to trigger hydrogen-assisted failures. And last but not least, of course, hydrogen embrittlement could compromise the key role of hydrogen as next-generation energy resource. We already have hydrogen-fueled cars, trains, buses in the market, and you can imagine how problematic it's going to be to store and transport hydrogen to fuel all these applications and to deliver the promises that the politicians are making in terms of the hydrogen economy to tackle the energy crisis and climate change. So, yeah, I think it's clear by now for everyone that this is quite an important problem. So you may wonder at this stage, how can it be that almost 150 years after Johnson's paper in the Proceedings of the Royal Society, not only the problem is still unsolved, but hydrogen-assisted failures are becoming more and more frequent. Well, there are multiple reasons for this. One of them, or maybe the main one, is that it's quite a challenging scientific and technological problem. It is quite a complex, multidisciplinary problem. It crosses the boundaries of material science, mechanics, chemistry, and it's quite complicated. So we do know the basics. We know that hydrogen atoms enter the material, they migrate through the crystal lattice, and they're attracted to areas of high hydrostatic stress or high volumetric strain, where there's more space for the hydrogen to fit in. However, then hydrogen in the fracture process zone interacts with the material in many different ways and at multiple scales. And this is quite a complex process. It changes the bonding strength between metal atoms, it changes the dislocation mobility, it facilitates the creation of vacancies. So there's multiple effects that are happening here, and the physical picture is complicated. And that is, of course, a challenge because we don't want to learn by observing accidents, right? We don't want to learn by experience. We want to understand what is happening so we can develop new materials that have an intrinsic resistance to this phenomena. And at the same time, we also want to develop models. We want to be able to predict what's going to happen. We want to be able to make decisions. So we want to decide which is the safe material that we want to use under certain conditions, which would be the dimensions of our pipeline. We need to know that information beforehand. So we want to develop these computational models. And this is, of course, also a big challenge for pipeline engineering, of course. Here you can see a screenshot from one of, again, another very popular newspaper in the UK, where they speaking about these large-scale trials that are going on to assess the suitability of our current gas pipeline infrastructure to transport hydrogen or a blend of hydrogen. And there are similar trials going on in several places in the world. I know one in Germany, for example, now. And basically, what these very expensive trials are trying to answer are the following questions, right? The questions that I have here. At what pressures can we transport hydrogen safely, and at what purity? And these are, of course, important questions. And what I will try to convince you today is that we can finally use computer models to provide answers to those questions. And that will, of course, have a very significant impact on costs. We will definitely minimize costs in that way. Because the scientific understanding is mature enough, and we have developed appropriate computational tools to be able to answer those questions. So let me tell you a little bit of my journey in trying to develop a predictive model for hydrogen-assisted fracture. And I think that I can divide my efforts into 4 stages, so to say. The first one is related to crack tip mechanics. So we know that the critical variables in this problem are the local crack tip stresses and the hydrogen concentration. So we need to make sure that we resolve the critical variables or the critical distance. We need to understand what is happening there. The second stage is related to the chemistry. We want to be able to capture hydrogen transport and surface reaction. So we want to know basically how much hydrogen we have, where and when. The third one is related to developing a mechanistic understanding of hydrogen-assisted cracking. So as I said before, hydrogen is a very complex problem that interacts with the material in multiple ways and at multiple scales. So it is key to be able to identify what are the critical mechanisms. We will never be able to model a pipeline atom by atom, so we need to make some decisions, we need to make some assumptions. It is important that we identify what are the first order effects, what are the key ingredients that we need to incorporate into our model if we want to capture the physics. And then finally, once we get the physics right and the chemistry right and the mechanics right, then what we need to do is to couple all of this into a coupled framework that is able to simulate complex cracking processes as we see in real scale applications, and is able to do that over the long time and space scales that we see in engineering practice. So we don't just want to deliver a computational method that can solve some funny academic problems. We want to be able to deliver predictions over scales relevant to engineering practice. We want to bring that virtual testing paradigm that has been a massive success in automotive industry to hydrogen sensitive applications. So let me elaborate a bit more on each of these ingredients or each of these stages of the model. So the first one is related to this crack tip mechanics, or resolving the critical variables over the critical length. And there's always a trade-off here, of course. So we want to be able to tackle engineering problems, so we want to use what we call continuum models. However, we also want our predictions to be reliable, so we need to resolve the physics. We need to capture the physics to trust our predictions. And if all the magic is happening in the first 3 atoms ahead of your crack tip, then you need atomistic resolution to resolve your problem. So what is the critical distance for hydrogen-assisted fracture? Well, we know the critical variables, that is hydrogen concentration and the stresses. Let's figure out the critical distance. And we can do so from experiments. There are multiple ways we can do so, but one of them, I think that is quite visual, is from experiments. So if you do a fracture experiment with hydrogen, you'll get a response like this. So this is crack speed versus stress intensity factor or crack tip load, so to say, right? So you can see that there are 3 stages. In the first stage, the crack speed changes quite significantly with applied load. As you increase the applied load, you increase the crack speed. Then there's a second stage where the crack speed is completely independent of applied load. And then finally is the rupture stage. And the reason why we have this second stage here, you can see here in the experiments, is because at this point, cracking is diffusion control. So cracking occurs in a rather intermittent manner. So the crack is sort of jumping. And for the crack to do the next jump, the crack needs to wait for the hydrogen atoms to go from the crack tip or from the crack surface all the way to this critical distance. This means that since we know how long it takes for the hydrogen atoms to travel a certain distance, we will be able, by measuring the crack speed in an experiment, to indirectly determine how long those atoms need to travel. What is this critical distance ahead of the crack? And yeah, as I said, you can take this, for example, this 1D diffusion equation. So this tells me the distance that those hydrogen atoms travel is equal to 2 times the square root of the diffusion coefficient of the material and the time. And then we do an experiment, and then we can see this is the crack speed for different applied potential. This is taken from one of our papers. This is a nickel superalloy. And for example, if we take these 3 replicate experiments here, we get a crack speed of 0.04 microns per second. Since we know the diffusion coefficient of the material, we can measure it. Then we can take into account this and the crack speed, and that gives us 2 equations. And by substituting, we get a critical distance of 1 micron. So this is roughly what you would expect, a critical distance of a few microns ahead of the crack tip. So that is the critical distance of our problem. And then if we go back to the drawing board, then that tells me that ideally I should be using some sort of discrete dislocation methods. But again, I'm not going to be able to model this with this. So the approach that we can take is that we can enrich our continuum models with the physical mechanisms that we're missing at the microscale. And the physical mechanisms that you're missing at the microscales that you see when you use these dislocation models is that you have some dislocation hardening mechanisms very close to the crack tip. These are due to plastic strain gradients and geometrically necessary dislocations. And the good news for us is that a good number of scientists have been working on this area. They have been developing what they call microscale plasticity or strain gradient plasticity models to be able to go beyond von Mises and conventional continuum plasticity models to capture those dislocation hardening mechanisms. And if you plot the tensile stresses ahead of a crack, this is the distance ahead of the crack, so here's the crack tip. What you see is that far away from the crack tip, those dislocation hardening mechanisms don't play a role, and you get the same results. But then as you approach the crack tip, and particularly when you are in this region where hydrogen-assisted fracture occurs, then you see that your stresses can be 2, 3, 4 times higher when you account for these dislocation hardening mechanisms. And that is important, of course, for 2 reasons, not only because failure would occur at a critical stress, but also because the amount of hydrogen that will accumulate will depend on the hydrostatic stress, as I mentioned before. So that takes me to the second ingredient, the chemistry. We want to be able to capture how much hydrogen we have, where and when, as I said before. So we solve 2 problems. One is the deformation of the solid. This is the standard balance of linear momentum. And then we solve an equation for the transport of hydrogen. So hydrogen is traveling within the metal according to this, which is an extended version of Fick's law. And you can see the coupling with the mechanical problem very clear here, right? So there's the gradient of this hydrostatic stress here. In fact, if you get the steady state solution, you'll get something like this. And you see that the hydrogen concentration will depend on an exponential term where all of these are constants. This is temperature, gas constant, partial molar volume, and this is the hydrostatic stress. So it is very important to get this term right. And in fact, when we couple this deformation diffusion model and we predict the hydrogen concentration ahead of a crack, you can see that with conventional continuum models, we're okay until we get to this distance ahead of a crack tip where we see a much higher hydrogen concentration. And we have tried validating this with experiments. It is difficult to find experimental data at such short distance ahead of the crack tip, but there are some. And the agreement is very good, which is very promising. And basically what you can see here is that only by accounting by those dislocation hardening mechanisms, one is able to capture 2 things that you see in the experiment. One is that the concentration of hydrogen increases with the remote load. And the other one is that the concentration of hydrogen increases as you approach the crack tip. So this looks promising. And as you say that the equation that I was showing before, that extended version of Fick's law, is the simplest one can use to model hydrogen diffusion. But in reality, we know that metals are not perfect. They have defects. So hydrogen not only travels through the metal, but also likes to sit in maybe carbides, dislocations, grain boundaries, and other defects. So one can, and we have done that. We have developed extended models that account for multiple traps, so we can predict exactly what is the partition of hydrogen, what is the hydrogen sitting, basically. And there's one last thing I want to say in regards to the chemistry. All these models rely on a boundary condition that is related to the hydrogen concentration. So we need to tell the model how much hydrogen we have in the crack surface. And this is easy to do when you have hydrogen gas, because you can use Sievert's law, and then you can come up with an expression that relates the hydrogen concentration in the crack surface with the pressure, with the hydrogen pressure. But when you are in aqueous electrolytes, then you need to resolve the electrochemical diffusion interface. And this is some of the work that we're doing now. We want our models to be useful also in offshore engineering. So we're trying to determine for a given defect size and a given electrolyte and a given environment, how much hydrogen is actually coming inside of the metal. And that takes me to the third ingredient, which is developing this mechanistic understanding of hydrogen embrittlement. And the key question that we want to answer is, how does hydrogen make metals brittle? What is happening that results in this big change from ductile fracture to brittle fracture? So you can see here, right? What is happening that you have this, in the absence of hydrogen, you see these very microvoid-driven ductile fracture processes. But suddenly, the moment you introduce hydrogen into the picture, what you see is very brittle fracture processes with hydrogen accumulating in the grain. Well, with hydrogen basically making this sort of grain boundaries weaker, or cracks propagating through the grain boundaries. So how can it be? What is this intergranular fracture process? What is happening that triggers this? And there is three aspects that I think are key to explain our rationale. The first one is that when you do atomistic calculations, DFT or molecular dynamics, what you see is that the fracture energy or the atomic bond energy is significantly reduced with hydrogen occupancy. These are some results for nickel. And you can see here fracture energy versus hydrogen occupancy. And you see that if your, let's say, grain boundary is full of hydrogen, occupancy of 1, then you have a 40% reduction in that bonding strength, in that fracture energy. So the grain boundary strength is going to be 40% weaker if you're full of hydrogen. So then the next question, of course, is how much hydrogen is actually in my grain boundary? Because if the occupancy of the grain boundary is low, then there must be other mechanisms that are playing a role. And the answer to that comes from the thermodynamics of trapping. So we know that Oriani allows us to plot the lattice hydrogen concentration as a function of the binding energy. So how energetically favorable is for the hydrogen atom to sit in that microstructural trap, and also versus the trap occupancy, right? How full the trap is going to be. And what you can see here is that for strong traps like grain boundaries, which is binding energies of -40 or smaller, very little hydrogen concentration is enough to fill the trap. You can see occupancy is above 0.95. So my grain boundaries are essentially going to be full of hydrogen. It is very energetically favorable for my grain boundaries to be full of hydrogen. And then if I go back to atomistic calculation, that tells me that I'm going to see a strong reduction in the fracture energy of this, or the strength of that grain boundary. And this is, by the way, what they see in the experiments. This is a recent science paper from last year where they did atom probe tomography. And this red thing here is the grain boundary. And you can see that there's quite a lot of hydrogen atoms that get accumulated in the grain boundary. It's just full of hydrogen atoms, basically, the grain boundary. And the last ingredient is to couple all of this with this enriched crack tip mechanics description that I was showing you before, because we know that grain boundaries are actually quite strong. Maybe the grain boundary strength will be on the order of 10 times the yield stress. So in the absence of hydrogen, our stresses, even if you account for those dislocation hardening mechanisms, are not going to be high enough to reach the cleavage strength. So you will need this ductile fracture process. You will need those microvoid cracking mechanisms to see failure. However, the moment you bring hydrogen into the picture, those grain boundaries are going to be full of hydrogen. You're going to drop your cleavage strength by 20, 30%. And then your stresses, when you account for those dislocation hardening mechanisms, those stresses that you get at that critical distance are big enough. And these two lines cross, and then you have a story. You have a rational interpretation, a mechanistic interpretation of how you go from a ductile fracture process to a brittle fracture process. And the good thing is that you have that without any fitting parameters whatsoever. We don't need to put any flag saying, hey, now you change. No, this comes naturally. You need to do an atomistic calculation offline. That's all you need. And this comes naturally into the picture. So that takes me to the last ingredient, which is developing this multiphysics modeling framework. And as I said before, I want to be able to model complex phenomena. I want to be able to model cracking problems of arbitrary complexity. And in order to do that, I need to make sure that my framework is quite compelling. And one paradigm that I want to introduce here is what they call this phase field paradigm, because many of these problems are interfacial problems. Of course, we need to track a crack. So that's an interface between a solid and a crack. And we need to be able to track multiple cracks, maybe multiple cracks interacting. So we need a powerful method of doing so. And the good news for us is that there's this phase field paradigm that has become recently very popular in the scientific community. And it's a way of basically discretizing interfaces and tracking them. Whenever you have an interface, you can assume has a zero thickness, as you see here. So we have two faces, the blue and the red one, and then you may have an interface with zero thickness. Or you may diffuse the interface, you may assign it a finite thickness, and then use an auxiliary variable, this phase field variable, to track where the interface is. And this tracking variable, this phase field variable, will go from 0 in one of the interfaces to 1 in the other, and will vary smoothly in between. So it allows me to tell me where my crack is going to lie. And there are multiple benefits associated with this. You define the equation in the entire domain, so you don't need a special treatment. You can capture topological changes like division or merging very easily, automatically. And then you can couple this with other physical phenomena, equations describing other physical phenomena. So it's very well suited for multi-physics problems. And this is something that we have exploited. And phase field has been a revolution in many areas of science and engineering. Two very famous ones are microstructural evolution. It is the most widely tooled now in microstructural evolution, and also fracture mechanics. You can see here very complex cracking patterns, right? Branching from secondary sites, merging of cracks, deflection, arbitrary crack trajectories. These are things that we couldn't dream of simulating years ago. And then, of course, the next question comes is, okay, Emilio, you have convinced us. The phase field is very powerful computationally, but how does this interface evolve? How does this phase field evolve? Well, the good news is that this phase field paradigm also brings a computational framework to Griffith's energy balance. So this takes me all the way back to the beginning of fracture mechanics. So as you know, Griffith postulated that a crack will grow if the energy released by the solid was equal or larger than the critical energy release rate, or the toughness of the material. And you can express the Griffiths functional in a variational form, and then you only need to minimize this functional to solve your problem. But the issue here is that we have a crack surface that we don't know. That is an unknown part of the problem. But using this phase field paradigm, we can track this crack surface. So the phase field paradigm, in a way, is a little bit like a damage variable, right? It goes from 0 in the solid, in uncracked material points, to 1 in fully cracked material points, so inside of the crack. And you can see that it converts this surface integral, becomes a volume integral, and it's a non-local model, which means that our predictions are mesh independent as long as you resolve this length scale. And then you can also see that it degrades the stiffness of the solid as continuum damage models. But basically, at the end of the day, what you have is two equations, one for the balance of linear momentum, so the standard deformation problem, and then an evolution for the phase field, which is basically a competition between the fracture energy and the strain energy density of the solid that evolves with applied load. So it is the thermodynamics of fracture coming into play. So it is a method that is physically sound and at the same time is computationally very compelling. You can see here an example where cracking is driven by the waves. This is dynamic loading, so that's why you see this funny cracking pattern. The red color denotes the cracks, by the way, and blue is intact material. And you can see that very complex cracking patterns can be solved just by solving this equation. So it's a very powerful method that is also physically sound. So it's quite convenient, and we have used this quite significantly. So at the end of the day, you have three equations that you're solving. You have one equation for the deformation of the solid, where you normally solve in finite elements, another one for the hydrogen transport, and then the damage. And they are somehow coupled, right? So as you increase the load, you'll have higher strain energy density, so higher probability of cracking, and then higher hydrostatic stresses will also accumulate hydrogen. But how does the hydrogen affect the damage process? So the way to do that is quite straightforward. You will basically define the toughness of your material dependent on the hydrogen concentration. And this is a very natural way of doing it, because this is what experiments show you, right? That the toughness of your material is dependent on the hydrogen concentration. Of course, the key question is what kind of degradation function do you define, right? How do you degrade that toughness as a function of hydrogen concentration? Well, the good news is that this is a universal framework. It can accommodate any mechanistic interpretation. You can define this degradation function as a function of the total hydrogen concentration, the lattice hydrogen concentration, the hydrogen concentration in grain boundaries, the dislocation density, or many of these variables. So it can accommodate any mechanistic interpretation. And I emphasize this because there has been also a little discussion in the literature, in the hydrogen-assisted fracture literature, regarding different mechanisms and the role that they play in different materials and environments. And I think this is important to know, that you can accommodate whatever you want. What I do here, in order to provide this mechanistic understanding, is to connect with that third ingredient that I was showing you before. So I'm solving for the hydrogen concentration in the lattice, so I know exactly how much hydrogen I have. That tells me also, using these Oriani equilibrium equations, I know exactly how much hydrogen I have in my trap, in my critical trap, in those grain boundaries. And then I can go to these atomistic calculations And these are done offline. I don't need to run an atomistic calculation, but that tells me quantitatively how much my fracture energy is going to be degraded. So the fracture energy of my facial evolution equation is going to depend on the hydrogen coverage, which comes naturally from the simulation, and then on this hydrogen damage coefficient, which is something that you get from the atomistics. In this case, for nickel, is equal to 0.41. So no fitting whatsoever, no bells, no whistles. Everything is dependent on, as a natural outcome of the simulation. Another thing that we want to, before I show you some results, one last thing that I want to say is that we're interested in happening also what happens once the crack has initiated. So whenever we have a sample exposed to a hydrogen environment, for example, hydrogen gas or an aqueous electrolyte, as you can imagine, the moment the crack propagates, that environment is going to follow immediately. So the seawater will immediately occupy the newly created crack surface. So we need to be able to capture that, and we do that with a penalty approach. You can see here how the crack propagates and how the hydrogen concentration is following, and also accumulating here where the hydrostatic stress is high. So let me show you some representative examples to show you what we can do with these tools. What you're showing here is R curves, so crack growth resistant curves. The vertical axis is the sort of applied load, a measure of applied load versus the crack extension. And you can see here the trend that you will see in experiments. So as you increase the hydrogen content, then you reduce the fracture resistance of the solid. Here I'm showing the influence of the loading rate, again an R curve. And you can see again what you expect to see from the experiment. So if you load very slowly, then there's enough time for the hydrogen to travel to the fracture process zone, and then you see a smaller resistance of your material. So we can capture those well-known effects. But let me show you also that we can also deliver quantitative predictions or quantitative agreement with experiments. These are experiments done in some steel bars that have been pre-charged with hydrogen and have a notch. And you can see that our model fits very, very well the predictions of the experiment in terms of notch tensile strength versus hydrogen content. Very good agreement. These are a set of maybe more interesting experiments. These were done in Norway by the group of SINTEF. What they did here, you can see they have a seawater bath. And what they did is that they immersed some metallic samples. I think this is a duplex stainless steel into this seawater bath. And then they subjected each of the samples at a different load. All of them at a constant load, but at a different loads. And what they were hoping is that some of these were loaded at a remote stress that was small enough such that no matter how much they weighted, it will survive. And as a result, they could deliver what is this threshold stress level below which you can load your structure safely. However, as you can see here, the symbols are the experiments. All of them fail relatively early. But the good news is that we can take our model, we can run first of all, we can reproduce the experimental data, and then we can run very large virtual experiments over very large time scales, and there we can tell them what is the critical load below which you can subject your structures safely. And we can do anything that we want. We can do so one thing that we could do, for example, we can optimize experimental campaigns. We can run standardized tests. This is an example of a rather complex test that involves a screw inside of concrete, a metallic screw inside of concrete. You know that hydrogen embrittlement is quite problematic for screws and bolts. So this is one classic example when you expose the screw to a quite aggressive solution. And you can see that with our numerical model, we can determine exactly what concentrations of hydrogen will trigger this, what kind of hardness of the material will trigger this, and we can capture the entire failure of the screw. And this sort of agreement with experiments gave us confidence to tackle more practical engineering problems, to enable that virtual testing vision that I was saying before, and that is in the title of my talk. So these are some toy examples here. You can see a pipeline here. You can see some cracking due to pit nucleation, and this is a pad eye made of high-strength alloy. But more excitingly, we can couple this with inspections, with non-destructive evaluation, and we can create what is called this digital twin of critical infrastructure that we want to simulate. So what you see here is a 12-kilometer pipeline that has been characterized by La Rosa and co-workers using ILI rendering. And these are what you see here in red are pits. So these are pit defects that they result due to corrosion, and were able to sample all those pits and their sizes and so on. So what we do is we simulate a critical section of that pipeline, 3-meter section, where most of these pits or most of the defects are accumulated. And you can see we have more than 100 of these defects. We can very easily introduce those defects into our model, because in these facial models, you solve for the facial as a degree of freedom. So you don't need to create a new mesh for every different pit distribution that you find. You have the same model for all pipelines, so that can save you a lot of engineering time. And then you just run, depending on the location of the pits, you just decide which ones will start with a phase fill equal to 1. But basically what we can do then is we can model those pipelines to the in-service conditions. And this is what you see in this video. You can see here at the top that when I load to the in-service conditions, some of these pits start nucleating, growing, and coalescing with each other. And eventually you get coalescence of multiple pits and complete failure of the pipeline. You can see it here. And I should emphasize that this looks a little bit like a video game, but it's actually quite a sophisticated calculation that involves multiphysics modeling and that is resolving pits that are on the order of hundreds of microns or smaller over a 3-meter component. And we can do that in a fully parallelized manner such that it runs in a few hours. So we have a tool that allows us to predict when cracking will initiate, how fast it will propagate, and when do we need to replace our component. Let me jump now to fatigue before I move to the corrosion part. We can also extend this framework to deal with hydrogen-assisted fatigue. So the idea is similar. You add a fatigue degradation function that degrades the toughness in addition to the degradation of the hydrogen concentration. This is a paper that we just published. And there's many things, many interesting things that we can do with this. One of this is we can compute virtual SN curves. This is what you see here. So these are two different materials. And of course, as you know, SN curves, they have a lot of experimental scatter. But you can see that we get a very good agreement with no fitting whatsoever with experiments just by adding the hydrogen into the picture. Other things that we can do is that we can predict Paris law behavior. And I should emphasize here that Paris law is not an input to the model, it's an output. We model cycle by cycle in these models, which means that we are able to capture arbitrary loading history. So we can capture the effects of arbitrary loading histories, and we can take as an output to the model the Paris law parameters, and of course the influence of hydrogen on these Paris law parameters. And we can also do virtual SN curves for, as I said, arbitrary loading histories or geometries, complicated geometries or arbitrary geometries, basically. You can see it here for a notch sample and for different hydrogen concentrations. So that takes me to the second part of my talk, which is what I will end, and I think I'll end at one time, so that's fine. What I want to talk about now is this pitting and stress corrosion cracking, so cracking driven by material dissolution. And this is another old problem that is quite relevant to, I think, the pipeline industry and offshore engineering. And it's also quite a challenging problem. Another of these problems that we have been trying to learn about and doing experiments for a long time, but we never really thought we will use computers to simulate them. And it has many similarities with hydrogen embrittlement, right? It is an interfacial problem. It is a multiphysics problem. So it is something that we are interested in showing that we can do with computers, but again, comes with multiple challenges. One of the challenges is the interface nature of the problem, right? You can see here, these are pitting in stainless steel as measured using X-ray. So this is a synchrotron, and you can see, of course, that it's very complex phenomena. You have pits and nuclei that start growing, and eventually they coalesce with each other. So mathematically and computationally, it's quite a nasty problem. The good news is that, again, we can make use of this phase field paradigm. Here, the phase field paradigm does not divide between crack and solid. Here, it divides between the aqueous electrolyte phase and the solid phase. So you can go from seawater when phase field is equal to 0 to the metal electrode when you have phase field equal to 1. And I won't get into the details for the sake of time, but basically you have two equations that govern the short range interaction. So the metal atoms detaching, so to say, this is what you use the phase field for. So this is the activation control corrosion, the process of the reactions that are happening there. And then you have the long range interactions, which you solve with an equation similar to Fick's law, where you basically calculate how the concentration, the diffusion of metal ions away from the interface. And as I said, I won't get into the details. You can find them in the paper, but everything is derived from the free energy based on thermodynamic principles and trying to be as physically sound as possible. And I will show a few examples. And what I want to show here is that the model can capture the main experimental trends. What I'm showing here is what they call this pencil electrode test. It's a classic corrosion benchmark. It's sort of a 1D problem. You have a metal within an epoxy layer, embedded within an epoxy layer. And then what you basically see is this metal corroding uniformly. So this is going to be an example of uniform corrosion. And the good thing is that you have analytical solutions for this problem in the case of diffusion control corrosion. And you can see here the kind of results that you will get. This is with Abacus. You can see that the corrosion front is growing as a function of time. And this is the distribution of the metal ions away from the crack. So you go from 0 all the way to the saturation concentration. And as I said, there are some analytical results, and you can see that the model reaches a very good agreement with those analytical results. And I'm just showing here in the slide very briefly that the model can capture activation control corrosion and diffusion control corrosion and the transition from one to the other. And this is captured through this mobility parameter here, which can be quantitatively related to the current density. So everything is physically based, and everything gives me physically based results. And you can see here that if you plot the pit depth versus time, you get a linear relation of activation control corrosion, but as you increase the current density, then eventually you get diffusion control corrosion. Then reactions are happening sufficiently fast, the diffusion becomes the dominant mechanism. And when you are in that regime, of course, then you see an influence of the diffusion coefficient. But let me just show you a few examples. This is a pit, for example, growing in a rather uniform way. And you can see that it agrees very well with predictions from the literature. And what I want to emphasize a bit more is that what we have done is to extend this theory to incorporate also mechanical effects. And there's two kinds of mechanical effects that we have incorporated. The first one is that, as argued by Goodman and many others, the corrosion current density is going to be related to the mechanical fields. So it's going to be enhanced by mechanical fields. And as I said before, the current density is related to the mobility coefficient, so we can easily extend that to account for those mechanical fields. And another important effect that we have incorporated into these models is the film rupture dissolution repassivation mechanism. We know that in most cases, you're going to have a film, and that is the problem of localized corrosion, right? The fact that you have a passivated film that is protecting from corrosion, but that passivated film is ruptured locally, and as a result of that, you get this localized corrosion. So we can capture that as well. And yeah, we can capture, I just want to say that we can capture pitting corrosion and pit to crack transition. You can see here sort of the pit to crack transition, which is something that I think in the corrosion community, we're trying to model with using finite elements for a long time. And we can do this in problems of arbitrary complexity. You can see a pit here growing in 3 dimensions. You can see here multiple pits interacting between each other. And you can, of course, also see here a quantitative comparison with experiments. At the end of the day, experiments are the ultimate judge, and we always make sure that all our model predictions deliver a good agreement with experiments. Here you can see this is the length of the corrosion damage region versus time, and these are for 2 experiments done at a different load. And you can see that we get a very good agreement with both, with no fitting parameters. And this is, we focus only on modeling only one pit, but you can model multiple pits, as I've shown you before. And this is on the same scale, and you can see that we get a good agreement in terms of the main defect shape and length. And just 2 slides before I conclude on what we have been doing lately. Extensions that we have been incorporating into these models. One is, of course, the electrochemistry. We want to model the electrochemistry. We want to be able to resolve the electrolyte, and we want to be able to model multiple ionic species. We want to be able to model the current density. We want to be able to model the electrolyte potential, and couple this with corrosion process, so we can capture the effect of changing concentration of species, pH, and so on. Another aspect that we're going to do, of course, and this is a natural extension, as you can imagine, is to couple the 2 parts of my talk, right? We have very sophisticated hydrogen embrittlement models that we've been working on them for many years now, and we have these corrosion models, so why not merge them together so we can capture also hydrogen embrittlement and stress corrosion cracking in these conditions where you have hydrogen coming in due to the corrosive reactions. So basically you could have cases where you change the applied potential, and then you go from conditions from anodic dissolution driven to cathodic fracture driven processes. And I think the basic idea that I want to say here is that I think there's several things that have happened in the past maybe 15 years that have opened this new modeling horizons, right? So I think it was, if you talk to people 10 years ago, they will tell you it was impossible to model these things. But now mostly we have more powerful computers, so we can run these multi-physics simulations. We can model how a solid deforms, how hydrogen travels through that solid, how the electrolyte is moving, how the metallic ions move into that electrolyte. We can model the fracture process, the fatigue process. We finally have enough computer power to solve those problems. And we know the equations that describe that physical phenomena. We just need to couple them. And then the other aspect is that all of these are complex interfacial problems. And with these facial algorithms, we're able finally to track how interface move with little effort on our side. It's quite a robust and powerful computational tool. So I'll just conclude with 3 remarks. I think the first one is what I was saying now. So recent progress in multiphysics modeling and interfacial modeling enable developing mechanistic models that can predict hydrogen embrittlement and corrosion damage. And this is a key point, right? Because one could argue that models have existed forever. We have some empirical models where people just did some back of the envelope calculations. But what is important here is that these are mechanistics models, or they simulate processes from first principles, so to say, right? You are simulating what is happening. You're simulating the mechanical damage. You're simulating each of the steps that are involved in the mechanical damage. So you gain a new level of understanding and you're much more confident on your predictions. And you can try different things. You can try the influence of the various aspects. The second concluding remark is that we're very happy that models provide a very good agreement with experiments. And not only they're useful for reproducing laboratory experiments or doing more targeted experimental campaigns, but they also deliver large-scale predictions. We can model applications of arbitrary complexity over very long time and space scales, over very large time and space scales. So we can deal with the complexity of engineering practice, which I think is quite important. So at the end of the day, there's an opportunity to extend the success of this virtual testing to hydrogen and corrosion sensitive applications. And this is kind of personal ambition and a vision, I would say, right? The science is sufficiently mature. The computational science, the computational engineering is also sufficiently mature. Then why not bring this change? We know that virtual testing changed drastically how we think about cars, right? That we don't crash cars anymore, or we crash very few cars. We don't crash hundreds of cars in the design stage anymore. We crash them in computers. Why not take advantage of this? And particularly when it's critical for something like the hydrogen economy, we're going to save much more money if we really take advantage of this progress in computational sciences. That's all. Thank you very much for your attention. I will just say that all the codes are openly shared, so you're welcome to go to my website, download them and use them. And of course, many thanks also to my sponsors for supporting my research and for all of you for attending. Thank you so much.
Thank you very much, Emilio. It was a great presentation, a lot of interesting stuff, and I can definitely endorse Emilio's work because when we started doing something on the hydrogen and brittle side, we were really in the middle of the ocean, and then Emilio's work kind of helped us direct us to do something on this area. And this is definitely a complex problem, but Emilio has done a great job. So thanks once again, Emilio, for doing this for us.
Thank you. My pleasure.
Yeah, and those who don't know me, my name is Shama Roy, and I'm the lead special projects and pipeline integrity at Northern Cross Incorporation. Apart from doing some exciting or complex pipeline integrity projects, as Farhad mentioned, our team is also doing some exciting work on hydrogen embrittlement and carbon capture and utilization, which is popularly known as CCUS. So feel free to reach out to us, any of us or the company, to know more about it.